In this video I will show you in an experiment what Kirchhoff's second rule is all about and how you can explain it properly using the law of energy conservation, and also of course what you can use it for when designing electronic circuits. And we will also derive the formula for connecting resistors in series, and I will show you one of the most common mistakes that is made when resistors are combined. My name is Andreas from The Fearless Engineer, and here we go. Now, the two rules of Kirchhoff, they belong to the fundamental laws in electrical engineering, alongside Ohm's Law and a few selected others. And in the last video, we already talked about Kirchhoff's first rule, which was the so-called node law or node rule. And in this rule, it was stated that the sum of the currents flowing into a node must equal the sum of the currents flowing out of it. And when we write this as a formula, we get the expression sum over all partial currents turned IK equals 0. And for a node with incoming connections and outgoing connections, in this case two outgoing connections as shown here in the circuit diagram, this results in the following equation, which is I total minus I1 minus I2 equals 0. And it gets interesting when we bring the currents I1 and I2 to the right side and multiply both sides by the time t, which gives us the equation I total times t equals I1 times t plus I2 times t. And since the product of current and time describes the amount of charge being transported, it becomes clear that Kirchhoff's first rule is actually a conservation law, which means that the sum of the charges flowing into a node is equal to the sum of the charges flowing out of it. Or in other words, there are no sources and sinks for the electric charge within a circuit. Charges don't disappear and the number of charges remains the same throughout the circuit. So Kirchhoff's first rule is a conservation law for the electric charge, and the second rule, which is what we will be talking about now, is also a conservation law, not for charge but for energy instead. And where the first rule is about dividing current flow and about connecting components in parallel, the second rule is about dividing voltage and about connecting components in series. But before we start to look at the equations, let's first conduct a small experiment. And to do this, we first connect the red cable leading to the voltage source with the upper end of the first resistor, and then we connect the upper end of the resistor in the middle to the lower end of the left resistor using a white crocodile clip, which connects them in series. And then we connect the lower end of the middle resistor to the upper end of the right resistor, and finally we need to connect the black wire which leads back to the voltage source to the lower end of the right resistor, so that the circuit is closed again. And now we have a series connection of 3 resistors connected to a voltage source, and we are ready to conduct some measurements. And first we look at the current distribution in the circuit, and to do this we break the connection to the left resistor just like in the last video by removing the red wire leading to the voltage source. And then we connect the yellow measuring tips of the ammeter in such a way that the complete current flows through it, first the contact at the first resistor, then at the red cable. And we have now finished connecting the ammeter in series with the resistors, which means that we can now start the actual current measurement. And you can see that the voltage source is set to 10 volts and also limits the current flow to a maximum of 100 milliamps to ensure that no heat damage occurs. And when we finally switch on the source, we measure a current flow of 1.46 milliamps, which is now running through the circuit. In the second measurement, we remove the ammeter from the first resistor again, reconnect the original crocodile clip and conduct the same measurement again at the other end of the circuit. And to do this, we remove the black crocodile clip from the lower end of the last resistor, attach the test cable, then also connect it to the black clip, and not surprisingly, the measuring device also shows a current of 1.46 milliamps, which was to be expected because the charge carriers have no way of leaving the circuit on their way from the left to the right terminal, which means that we can derive our first insight, which is that in a series connection the current is identical at all points within the circuit. And in the next measurement we will now focus on the voltage, and we will measure it 4 times now across each individual resistor and across all resistors combined. And for this purpose the ammeter has been removed from the circuit again, so that the measurement is not being changed by an additional component here. And so in order to measure the voltage drop across the resistors, we now switch the multimeter to DC voltage measurement, and then we press the 2 test probes firmly onto the upper and lower ends of the left resistor to measure the first voltage. And from the display we can read a value of minus 4.78 volts and the negative sign, which you might have noticed, by the way, this comes from the fact that I have connected the COM port of the voltmeter to the positive terminal of the source. Actually, it should be the other way around, but we are only interested in the amount of voltage at the moment, so the sign doesn't matter yet. It will matter later in other experiments, but for now we're only looking at the absolute measurements here. And by the way, the left resistor has a value of 328 ohms, which we have already determined previously in the video on Kirchhoff's first rule. And now we do the same again for the resistor in the middle, and we get a voltage of 4.757 volts, which is much higher than with the left resistor. And then we measure the right resistor, and here we observe the same voltage values as in the middle, which is also 4.757 volts. And by the way, both resistors have the same value of 3,267 ohms, which we also know from the video on Kirchhoff's first law. And finally, we measure the voltage drop across all resistors combined. And to do this, we press the first measuring tip against the upper end of the left resistor and the second tip against the lower end of the right resistor. And when doing so, it's important that enough pressure is built up with the measuring tips, because otherwise the values will fluctuate. And after the measurement has been stabilized, the display shows a value of minus 9.99 volts, which is almost identical to the source voltage of 10 volts. Okay, so that was the first series of measurements, and now let's have a look at the results. And in the table here on the slide, you can see all the measurements we have taken so far, and as you can see, the voltages across the resistors, they correspond very nicely to the predictions which we made using Ohm's law, which you can see in the right column. And just as with Kirchhoff's first rule, we can also deduct Kirchhoff's second rule directly from these values, and to do this, we only have to add up the partial voltages across the individual resistors. And when we do this, we end up with a result of 9.99 volts, which corresponds almost perfectly to the source voltage within the scope of the measuring accuracy we have here. And expressed in formulas, we can write down 0.48 volts plus 4.76 volts plus 4.76 volts equals 9.99 volts, or in more general terms, U1 plus U2 plus U3 equals U total, with the U's being the different voltages we have in our circuit here. And if we now move all the voltages to the left side of the equation and express it as a sum, we get the form sum over all voltages UK equals 0. Now let's take a closer look at this expression by using a circuit diagram. And basically what we've done with our measurement so far is this. We have followed the path of the current from one terminal to the other and adding the partial voltages along the path. And by the way, the gray rectangles to the right of the resistors shown in the diagram are perfect voltage meters, which have an infinitely large internal resistance, which means that at least within this simulation here, they give us the voltage drop across the resistors without affecting the current flow through the unbranched circuit. And when summing up voltages in such a way, two things are important here. The first is we have made a complete cycle through the circuit, which means that we have arrived at the same position from which we have started. And secondly, we did not pass any point in the circuit more than once, but instead we moved straight from the positive terminal to the negative terminal. And based on this, we can find a formulation for Kirchhoff's second rule, which is often found in the literature and states that if you follow a path from one terminal of source to the other terminal, the sum of the partial voltages along this path is equal to the voltage of the source itself. And by the way, such a closed path is also called a mesh or a loop, and that's why the second rule of Kirchhoff is also called loop rule. And behind the loop rule, we can find another law of conservation, just like with the node rule from the video on Kirchhoff's first law. Multiplying the voltage U by the charge Q, which is transported through the circuit, yields an expression for the amount of work which is performed on the charges in the resistor, which is the amount of energy which gets converted into heat. And this means that we can rewrite the loop rule for a simple series connection here to Q times U total equals Q times U1 plus Q times U2 plus Q times U3. And based on this expression, we can also interpret Kirchhoff's second rule as follows. The potential energy which is provided to the charges by the voltage source is equal to the amount of energy that is transferred to the resistors along the path from the first terminal to the second terminal. And this means that Kirchhoff's second rule basically expresses the conservation of energy in the circuit. The potential energy of the charge carriers, which results from the potential difference within the source, is converted into kinetic energy. And if the charge carriers move through a component such as a resistor, the kinetic energy is converted into other forms of energy such as heat. And the sum of all forms of energy in the circuit is identical to the source energy at any given time. And if you don't understand why this is the case and what voltage and charge have to do with energy, then you might want to watch my video about work and also energy. Again, the link is coming up for you now. We can also display the partial voltages in a loop graphically, which looks like the diagram here. We start the loop left of the power source, where the voltage increases from 0 volt up to the source level, and when the charge carriers have passed through the first resistor, a part of their kinetic energy has been converted into heat energy, and the voltage level, which we also refer to as potential, has dropped accordingly. And as soon as the charge carriers have moved through the second resistor, the next drop in the voltage curve occurs because potential energy has again been converted into heat within the component. And after the third resistor, we have arrived at the voltage level of the source again, which in this example corresponds to 0 volts. And this means that the potential energy of the charge carriers has been completely converted into other forms of energy. And this is exactly the statement of Kirchhoff's second law, which states that the sum of all energies, and thus the sum of all partial voltages in a closed loop, is 0. But when we are moving through a loop to sum up the voltages, it's very important that we observe the signs with which the voltages enter the loop equation. Whether we have to choose plus or minus depends on the direction in which the current flows, and whether we look at an active component such as a source or at a passive component such as a resistor. And these two aspects, they determine the direction in which the potential difference changes. And in diagram A, which you can see here, the current flows from left to right, which means the potential energy of the charge carriers to the right of the resistor is smaller than to the left. And if we move from left to right in the direction of the current when calculating the voltage difference, then the delta voltage between these two sides, voltage on the right minus voltage on the left, is negative, and we consider the voltage drop in Kirchhoff's loop equation with a negative sign accordingly. And if we move through the loop as shown in diagram B instead, against the direction of the current, then we calculate the delta voltage by subtracting left voltage minus right voltage, and the sign in the loop equation is positive because the potential is higher on the side towards the source. And while we can choose the direction in which we move through a loop freely, basically, what really counts is the sign of the potential difference in front of and behind the component in the direction of the current, which is also the direction of energy loss for the moving charges. And if we look at a source instead of a passive component such as a resistor, then we do it exactly the same way. On the left side of the diagram C, which you can see here, the loop direction is again from left to right, while the source has its positive pole on the right side. And in the sense of conventional current direction, the potential on the right side of the component is higher than the potential on the left side. And because this results in a positive sign in the potential difference, which means that the voltage on the right minus the voltage on the left is larger than 0, the voltage source or the source voltage enters the equation positively when moving from left to right. And if you're not sure why this is the case, you might want to watch my video on the difference between conventional and physical current direction. The link is coming up for you right now. And in diagram D, just as with the resistor, we can of course also move from right to left, which means that the potential in front, this is the negative pole in this case, is lower than the potential on the other side. So the sign becomes negative. And in order to reduce the potential for errors and to avoid confusion, my personal tip to you is always start at the source and proceed in the direction of current flow when moving through a loop. And in this case, the source voltage is always positive and the resistor voltages are all negative. And in case of a branched circuit, however, the different currents can also have different signs which you encounter, within the same loop even. But this is something which we'll look at in later videos. And before we finish this video, let's take a look at how we can derive the total resistance of a series connection. You might remember that for components connected in parallel, we were able to use voltage equality to arrive at the overall resistance. And for components in a series connection, we can now use current equality in a very similar manner. Let's take a look at a sample circuit here. You can see that 3 resistors are connected in series to a 10-volt voltage source, and from the voltmeters you can see that the sum of the partial voltages over the resistors is equal to the source voltage, which is basically what Kirchhoff's second law predicts to us. And by using this law, we can easily set up the loop equation in the form U total minus U1 minus U2 minus U3 equals 0. And just as with Kirchhoff's first rule, we can now use Ohm's law to replace the voltages by the product of resistance and current for each component here. And if we also move the partial voltages to the right side of the equation, we get R total times I total equals R1 times I1 plus R2 times I2 plus R3 times I3. And this is where the current equality comes into play, because if the current through all resistors is the same, we can simply divide by I total, by the total current on both sides, and we get the equation for the total resistance, which simply is R total equals R1 plus R2 plus R3. And this means that in a series connection, the sum of the individual resistances results in the total resistance. So we get the general equation form, sum over all partial resistances Rk equals R total. And here's one last test for you. Try to calculate the total resistance for the left loop of the circuit here, which means that you should start at the voltage source and then follow the path via R1 and R2 back to the source. Please try this for yourself and pause the video now, and afterwards we will have a look at the solution together. So pause the video. Okay, so what's your result? In exams, what we find are usually three typical answers over and over again. The first is 1100 ohms, the second is 300 ohms, and the third is 260 ohms. And is your solution among these? If so, let's take a look at the circuit again, this time with the total current and the branch currents. And from the total current and the source voltage, we can calculate the total resistance of the circuit, which amounts to R total equals 10 volts divided by 38.46 milliamps, which is equal to 260 ohms. So well done if this is your solution. And in case you have chosen answer B, then please take a look at the currents here, which are running through R1 and R2. They are not identical in this circuit, because the total current is divided at the upper node and splits into the two branches. And when we derive the equation for resistors connected in series, we could only exclude the current on both sides of the equation, because we assumed that it was identical, which is an assumption that does not hold for this example here. And if you got the result right, then be so kind and please drop me your solution as a small comment below this video into the comment section. You will definitely get a like from me, and maybe I can also give you a quick tip on how to solve such a task even faster in the future. In this video we have looked at Kirchhoff's second rule, which is also called loop rule. And just like with Kirchhoff's first rule, it is based on a conservation law, which in this case describes the conservation of energy in a circuit. And one consequence of energy conservation is that the sum of the partial voltages in a circuit with the same start and end point must equal 0. And in practice, this means that the loop rule can be used to determine unknown voltages or to calculate the total resistance of components connected in series, which also exploits the current equality in an unbranched circuit. And there are many more applications for this rule, which we will discuss in future videos. And in case the circuit is branched, you can additionally use Kirchhoff's first rule and combine resistors connected in parallel into a single resistor, which is in series to the rest of the circuit. And in one of the next videos, we will look at how Kirchhoff's first and second rule can be combined to create a system of linear equations which can be used to calculate unknown quantities very easily, even in more complex networks. But before we get there, let's first take a look at the voltage divider rule in the next video, which is a direct consequence of Kirchhoff's second rule and is another basic tool in electronics which you need to know about in order to design circuits. And as always, if you have any questions or requests for topics I should cover here, just drop me a comment and maybe I will make one of the next videos out of your ideas. And if you like the video, please consider subscribing to my channel. That would certainly keep me motivated to produce more such videos in the future. And finally, one last tip: you can download all my learning materials such as slides and circuit simulations and such from my website at thefearlessengineer.com. So that's it from me for now. Have fun and see you here next time on The Fearless Engineer.